Hey, Adnan.
Hey, how are you?
Good and you.
I'm
Thank you for
good.
responding today.
Yeah. Totally. How are you
Let's
doing?
see. So I took a another practice exam
Yep.
last Friday, and I got a 505. So I'm steadily.
Congrats. Nice.
That's like discouraging. It's not discouraging. It's a little discouraging. Is that my bio score is forever a 125? Like it's not moving. It's not going down, but it's not going.
Yeah.
It's just like
Well, not going down means that each time you do it, it goes up from zero. So.
I guess, but I don't know. I just
Ha-
expect improvement because like everything else improves, but bio.
yeah. I usually, it's because, all right. So like, the MCAT tests such a broad range of topics that, let's say you got something wrong on one practice test and you learned your mistake, it may
Mm.
not be test that same topic may not be tested again for like the 10th practice
Mm.
test. The sample
Okay,
size is too small.
that's true. So hopefully, like, because I feel like
What was your score
yeah, you're
breakdown for
right.
this test?
I can show you. Pull up my screen. Um, do this. Share screen. Okay. Okay. So I'm gonna go through all this stuff. Um, Yeah, because I feel like each test they like test different things.
Mm-hmm.
So it's like I get what you're saying with that aspect. I mean, some
Yeah,
stuff, like, yeah, you're
because
right.
like so like don't put too much weight on how you perform on the practice tests,
Hmm.
just because like the fact of the matter is that you're learning each time you take it,
Hmm.
so it's good to focus on the positive.
So this breakdown was pretty even, which I really appreciated because the last exam we went over, I told you that my what you call it my chem and my psych social went down, but because like I spent more time last week making sure I got these two in, and then also with your help with this section, like it went up 2 points to where I'm used to it being,
Yeah.
because yeah, I average a 125 126 in this, and then 127 is usually where I
Mm-hmm.
go. And same for this, I average 127 for cars. This cars was difficult, but like I wasn't surprised that I got a 127.
Yeah. All right, this looks pretty good. Let's see. Okay, so I noticed that you have not. Let's see. That you didn't flag anything for BB, or you're not flagging like too often.
Yeah, I don't flag. Um, I don't really need to flag stuff more times than not, just because I always finish my stuff on time, and it's always BB and psych soc.
Mm-hmm.
I average, I average about 20 minutes left over for psych soc and 15 to 25 for BB left over.
Okay.
I never run out of time for anything, honestly.
Okay.
Um,
So
but
yeah, what would you like to go over?
So I went over a little bit of it, but I did have some questions about it yesterday.
Mm-hmm.
And then the rest will probably be on the website. So for this one, we were talking about this, and I was just trying to understand what knowledge I like, fundamental knowledge I should know from this, because the explanation talks mainly about titrum, but like I never, as a chem major, learned in depth titrum. So I was like,
Oh yeah,
okay,
I learned this from the Tobey Maguire Spider-Man 2 movie.
oh
So basically, Doctor Octopus in that movie uses tritium. It's called tritium.
sorry, tritium.
So well, you probably remember from chem deuterium.
Yeah,
So
it's H,
tritium is just
right?
so wait, what's deuterium?
It's 2H,
Yeah,
right?
so it's basically just an extra neutron on a
It's
hydrogen, right?
heavy hydrogen. Yeah.
Yep. Tritium is then two extra neutrons.
Okay.
Yeah. And it's pretty like if you've ever seen it in real life, it like glows. Certain
Oh.
like weapons like guns have like a tritium kind of sight which glows
Mm-hmm.
in the dark and basically never, goes out because it
Mm-hmm.
glows pretty it gives off that glow pretty much for infinity.
Mm-hmm.
They even have some pretty cool necklaces that are made out of like some tritium. But yeah, so it's the same kind of deal with deuterium. They just label it to see like where how a mechanism works essentially. So
Mm-hmm.
you basically want to put it someplace where it'll stay, where it won't be removed.
Mm-hmm.
So all of the other sites, there's a possibility of the hydrogen being removed
Mm-hmm.
from, just because the amine is like kind of like a little basic.
Mm-hmm.
So it has a tendency to give. Oh no, wait. Oh, okay,
Okay.
cool. They're pretty organized.
Yes, I try. Okay, go ahead. Do you see it?
Yeah, yeah. So you basically want it to be at a place where it's not going to have any. There's not going to be any chance of it leaving,
Mm-hmm.
because yeah, it's pretty easy for an amine group to like get to take a hydrogen from like water or anything to be like NH3, right?
Mm-hmm.
So, and if you didn't know that, you can kind of like look at the fact that, well, Roman numeral 2 and Roman numeral 4 are pretty much the same.
Yes, which I knew. I was like, those are pretty much the same.
Mm-hmm.
I chose 3.
Let's see. Yeah, 3. So that would be like, so if they asked you a question, that would be like, what's the site for an enzyme to add some type of thing? Like, site 3 is like the best site for it to create a bond, like a peptide bond, or it's the most
Right.
reactive site. But
Yeah.
since we're talking about putting like a label on it, we want it to be the least active site.
What? So what? No, but sometimes like some labeling questions, like the one we went over last time, was for active sites so that it can tell like when it leaves or like
Mm-hmm. Yeah,
saying.
it seems like this is just to measure the rate of the biochemical processes that involve the binding or incorporation of the entire molecule.
Hmm.
So we just want to keep it on the guanine. So wherever we measure that tritium amount, we know that the guanine is there.
Okay. So I guess the safe answer would be like on an area that's not reactive and like these is the most reactive, and I'm assuming these two are also reactive in a way.
Yeah, pretty much. Because
Oh,
just imagine like the NH2 group, for instance. Um, that's at site 3. That's like pretty much almost like the NH3 or NH2 in like an amino acid, right?
mhm,
So
yeah, that's why
it'll
I
have
chose
a
it.
tendency to be like NH3 plus,
Hmm.
and then go back to NH2. So so basically like water can, so it can donate its lone pair to get another hydrogen to be NH3, like NH3 positive, and it can give away one of the hydrogens. And if we had if we had tritium there, there's just an easy possibility for it to be lost into the solvent.
Okay, yeah. So, but
Mm-hmm.
it's just that like with this question, like the wording didn't give me a clue. Like literally, if this question was like choose something that is not reactive, I would have chosen one. So it's like, how do I know, when I should be choosing areas that are reactive and are not reactive? Or should
Uh,
I have approached it like, oh, okay, which one's not like I don't, what I'm
yeah.
saying?
So if let's say that the question is like C14 labeling on, let's say, like glucose or something, and you wanted to see like where a specific carbon ends up, like eventually it'll be given off as CO2,
Hmm.
um after the Krebs cycle and after the electron transport chain. So that's
Hmm.
like a way that we know that all of the carbons that you consume are exhaled as CO2.
Hmm.
So that's gives you insight into like the mechanism. But this is talking about just the binding or incorporation of this entire molecule at large.
Hmm.
So you want it to stay on that molecule because we're looking about what happens to that molecule.
Hmm. Hmm.
So,
That makes sense.
mm-hmm.
So for this one, I got the answer right just because I took an educated guess. But I wanted to know the science behind it just so I'm not missing a fundamental.
Yeah, so electric field lines are just uniformly separated like arrows, like vectors.
Mm-hmm.
And if they're closer together, that means that the field strength is stronger than if
Mm-hmm.
they're further apart.
Mm-hmm.
So, but if they're uniform, it means that the electric field strength is the same everywhere within that field.
Mm-hmm.
So they're going to be equally spaced.
Okay.
So that's like just, when you draw like the vectors for a field.
Okay.
If you
So it's not.
remember like the thing that I may have shown you where I talk about electrostatic force and gravitational force, like
Mm-hmm.
side by side,
Mm-hmm.
and how they all, go towards like, they're all like tangent to like the planet or the point charge, and if you zoom in on that, they're all like, tangent to the ground. So yeah, so they'll be closely spaced if the field strength is stronger. They'll never intersect though.
Okay. So electric fields never intersect.
Field lines in general. So that goes for like gravity as well.
Never intersect.
And yeah, and also like think about them as like vectors essentially.
Mm-hmm. Stronger the force. Okay. Um. This one.
Can you zoom in a bit?
Yes. For this one,
Mm-hmm.
I messed up on this one. But basically, I understand that you're supposed to multiply like do because if you look at the units, you have to do like 0.67 moles times.
Micromoles, right?
Yeah, sorry, micromoles
So
times.
you would turn that into, oh well, they give you a value for
Yeah,
micromoles, so you could just use that. You don't have to do it.
right. But the part that confuses me, when Jennifer explained it, was
Oh, and then
doing.
2 electrons, I think,
Yeah,
for
I
each
didn't get
thing.
that part. Like
I see that
that.
up top where it says reaction to a 2 electron oxidation.
Yeah, I get that, but I'm just like, why? And like, it was just like, what? You know what I'm
Mm-hmm.
saying?
Oh, yeah. A lot of things like, for instance, like, yeah, a lot of things have like a 2 electron like oxidation. Like, think about it, like NAD plus, and then it turns into NADH. That
Hmm.
H, by the way, is a hydride. It's not, a proton. It's basically a hydrogen with 2 electrons.
Okay.
So that hydride is what adds to like NAD plus and FAD,
Hmm.
and that means that it's the addition of 2 electrons.
Right.
Mm-hmm. So yeah, they're just saying that reaction 2 is a 2 electron oxidation. So each time it goes from D-glucose to compound 4, 2 electrons are basically being lost.
So like, but the thing is like, we divide. So you do that, and then you divide it by two. But like, why don't you divide it by two times the number that's for electron mass? You know what I'm saying?
Oh, wait, let's see. So, well, it seems like, okay, so like, let's see. They're asking, okay, the mass of the glucose. So basically, I would do like the 0.67 micromoles of electrons and multiply it by, in parentheses, by, um, let's see. Oh, like
180.
one molecule, I guess, or like 1 mole of glucose over 2 electrons.
Uh huh.
So the electrons cancel out, and then I would multiply it by, um, the 180 grams per, or like what 180 micrograms per micromole.
Mm,
Is that what you
okay.
ended up doing? So that would be like 0.67 divided by 2, which is like
Yeah,
3
it was
point, like
like.
0.33 times 180, which is like 180 divided by 3, which is like 60. Is the answer B?
Mm-hmm.
Yep.
Okay. I'll just make sure to look out for like stuff like that in the future.
Mm-hmm.
So for this one, I was never really good at this type of stuff. Um,
Let's
yeah.
see. Okay, so remember. Okay, so okay. pH of a 1 liter phosphate buffer solution was measured at 7.6. So this is any type of buffer is like a weak acid. So remember the Henderson-Hasselbalch? And then they say, okay, the pKa values for phosphoric acid, it's a triprotic acid.
Right.
So, okay, let's see. Which method, wait, but the experimental, okay, so okay, we have a 7.6 pH, we want it to be 7.2, so if its pH is equal to pKa plus that log term, right, we want that log term to be negative, right?
Right.
Because we're going to subtract from the pKa. Well, if the pKa is, okay, let's see. If it's 2.2, then you want it to add. You want to add 5. If it's 7.2, you want to subtract by 0.4. So that's what you want that log term to be, like negative 0.4. And if it's 12.3, right, you want it to subtract as well. So let's see. If it's at 7.6, right? Like now we have to determine which pKa value to use. If the pH is at 7.6, then it should. So that means that it's okay. So if the pKa at 2.2, and it's put in a pH whatever that's 7.6, it's in a basic environment, so it'll lose its proton. And then since the second pKa value is 7.2, it'll lose its proton again. So it'll basically lose 2 protons. So which method will adjust the solution to the proper pH? Let's see. Add enough. Okay, that's just HPO3. Like anion. So if that were the case, then you would have the top of that log term be 10 times that of the bottom. So log of 10 is 1, and it would basically be, and since it's HPO3, that's like the 7.2 one, because it still has 1. It lost 1. I'm sorry, it lost 2.
Yes.
So it'll be like 7.2 plus 1 or 8.2. Oh wait, sorry. 7.2 that pKa plus 1, so 8.2. So that's not going to work. Let's see. Add 1 molar sodium hydroxide to neutralize a portion of the hydronium ions found in the solution. So I mean that would. Well, we want a lower pH, so we don't want to neutralize anything.
Exactly.
So, okay, that's out. And I'm just going to look at D. Add 100 milliliters distilled deionized water to dilute the basicity of the buffer.
I thought it would make it more acidic if you dilute the basicity.
If you dilute the basicity, but we have to see exactly like how much. So they're basically making, so your new volume would be 1.1 liters of the phosphate buffer. So okay, I think that would be like, that'll be like 0.1, and the log of something like that, that's between 0 and 1 is negative. So okay, that if the math works out, that can maybe work. Let's see. C. Alter the ratio of monosodium to disodium phosphate. Added to favor the monosodium species. So that's basically H2PO3. Like NaH2PO3. All right. Now, so, okay. If that is the case, so that's H2PO3 over 8 HPO3, I suppose. So you're adding more of the. So the H2PO3 one is the one that has the pKa at 7.2. and the HPO3 has the pKa at 12.3. Let's see. So, all right. I mean, C involves you making it. So if you alter that ratio to favor the monosodium species, you're making it favor the H2PO3 one, which has a pKa at 7.2. So it should be changed from like 12.3 to 7.2, and so that's a possibility. And then D would dilute it. So, you know what? Since pH is just based on... Wait. Hydronium ion concentration, negative log of that. Concentration... it's saying that... Okay, alright. So, it's saying that adding strong base, diluting with water, or adding a different basic salt will not lower the pH. I'm trying to think why that would be. Because if it was Henderson-Hasselbalch, then you would just have, concentration of conjugate base over the acid. Alright, so I think that if you add that, like, distilled water, it'll add to everything. So it actually, I don't think it would change the concentration. Because, like, the conjugate base concentration would be the amount of that conjugate base, molecules, or moles, rather, over the total volume, right? And then that'll be the same for the acid concentration. So... essentially, the volumes cancel out in that log term for the Henderson-Hasselbalch.
Like, adding the water won't just change the basicity, it also change the acidity.
Wait, sorry?
Well, adding the water...
Oh, it won't change anything, actually.
Oh, okay.
Because I was thinking of... Because, negative log, like, whatever. Like, the... like, you know how it's like pH is equal to pKa plus log of conjugate base concentration over acid concentration? If you make the volume higher, it's going to affect the conjugate base concentration and the acid concentration the same way. Because that's just, moles of the conjugate base over liters of solution, and over moles of the acid over liters of concentration. It's going to change. It's going to change the volume, like, the same way for both of those.
Okay, that makes sense. Okay. So, okay, first, I think you need to look at this equation, or one of these equations. The question asks, what is the balance equation for the non-productive reaction when lysine is substrate? So, like, yeah.
Wait. Sorry, wait, say that again?
This is the question.
Balance equation for the non-productive reaction when lysine is the substrate, okay?
And then you would have to, like, look up here.
Let's see. Okay, let's see. 2 steps. First step, NADPH reacts with FAD to form NAD plus and FADH minus. So that's, like, quickly just an example of the hydride added. Because you see how it goes from FAD to FADH minus? Okay. Then FADH minus quickly reacts with O2 and H plus to produce FADH, OOH. pH independent, so it doesn't matter what the pH is, it'll be at the same rate. Okay, at this point, then it either hydroxylates compound 1 or decompose. Okay, so that's the non-productive thing. Decomposes non-productively to form hydrogen peroxide. If something like lysine. Yeah, sorry?
You said so after reading the decomposed non-productive part, that's okay, that's the non-productive. Okay.
Mm-hmm. Yeah, so that's when lysine. Yeah?
What does that mean?
I guess that means that it doesn't produce anything that is helpful.
It's just okay.
I guess it just it goes into hydrogen peroxide, which doesn't do anything, I suppose.
Mm-hmm.
So yeah, okay. So then let's see. That happens when lysine occupies the active site. So basically, we have FADH OOH plus something to make H2O2, I suppose.
So you said is.
Oh, I see. So like non-productive, because so like productive would be like making an electron carrier or something like that.
FADH.
Like FAD or something like that. Wait, what's that?
Oh, you said FAD. Okay.
Yeah, some like those. Most like metabolic reactions involve transferring electrons. Like if it's a catabolic one, right? Mm-hmm. Transferring electrons to electron carriers, which eventually gives it to oxygen.
Mm-hmm.
So, all right, let me see the choices. Where's D?
Well, I didn't capture that.
Okay. So, I mean, okay, so C doesn't have a product, doesn't have H2O2 as a product.
So in the reading it says to form. So I should cross that one out immediately. Dang. Okay.
Yeah, and then they said compound. Okay, so FADH hydroxylate. Okay, decomposes with H2O2. It's a two-part thing, so we have to put in that first part as well. And the first part I think was like NADPH to FAD. Mm-hmm. Let's see. Okay, so NADPH plus FAD makes NAD plus and
NAD plus.
Okay, and then it makes the FAD minus, but I wouldn't include that because it quickly reacts with O2 and H plus to make that thing, and then that thing turns into H2O2. So maybe like NADPH plus FAD yields H2O2, something like that.
Plus O2 plus H plus to form FADH OOH, and then
yeah, so like that would be the first step, and then underneath it I would write the FADH minus as a reactant. Plus O2 plus H plus to yield FADH OOH.
Yes, and then you do
and then maybe like a third part like underneath that where FADH OOH is on the left side, like the reactant side. And then I guess like it just, and then like an arrow for H2O2. So let's see. Yeah, is it A?
It is. I just have to like. I guess I'm just canceling it out.
Yeah. Something that is on the product side and reactant side for the next one, you cancel those out to get like the net reaction.
NADPH plus H plus O2. I have an FAD though left over.
Wait.
Because up here it says NADPH reacts with FAD, and I have an FAD left over though.
Let's see. Plus FAD yields that. Let's see. Okay. Let's see. Oh yeah. Wait. Okay, so I think it does. No, it does regenerate FAD.
Oh,
But
it says the pH depends on sex at which regenerates FAD. Oh, it says at the bottom, doesn't it?
yeah. So I just think that they didn't write it. Oh no. Because it would be as a product, and then it'll cancel from the reactant in the first step.
What product? You talking about what I just read?
Yeah.
Oh yeah.
So it does. It does. So you'll in the bottom in the last reaction on the product side, you'll have FAD.
Yes.
Yeah, and it'll cancel out with the reactant of FAD in the beginning.
Mm-hmm. There that is. Okay. That was H2O2. Okay. There's that.
That makes sense?
Yes. For this one, I knew that amic meant carboxylic, so I knew I had to choose between. How do I explain this?
All right, so I went over this yesterday, and so you know, like the passage actually shows you like the molecule.
Yeah.
And it's a general structure, so we just have the R groups there. Like we don't have to write out the entire thing. But it said something in the passage. It said something about the acetylation of the hydroxylamine.
Mm-hmm.
So that gets acetylated. So this R, to like the carbonyl group thing, is added.
That's the acetylation.
Yeah, because that's the acetyl group, right?
So this wouldn't count because that is a ether.
Ester.
I keep messing this up. Ester.
Mm-hmm.
So I keep messing those up every day. Ether is ROR.
Mm-hmm.
I don't know why I keep. Do you have any way of like remembering it?
Well, I remember that ethers are good nonpolar solvents,
okay.
and esters are kind of like, well, they come up a lot in like high energy bonds, like a phosphodiester bond.
Mm-hmm.
They're also in like a lipid when like the glycerol binds to like a fatty acid.
Mm-hmm.
And I like group them in the same category as like an amide, where an amide is just a nitrogen instead.
Mm-hmm. Mm-hmm.
Yeah,
okay.
so like we kind of have like an amide for like A, and then B is an ester, and then C we have that hydroxylamine group and an acetyl on the left, and then let's see, D. So okay, D just has like a carbon in between the acetyl and the hydroxylamine, so you want the hydroxylamine attached to the acetyl.
Mm-hmm. Okay. And then some mixers of acetyl is just why we were talking about these yesterday. Why can't it just be called like a ketone? Because that's what it is.
Oh, because ketone is a general term. Yes. But it's acetyl is a specific one. That's why, like, think about it with like acetic acid. Like in vinegar. So like carboxylic acid is like a general term for something that has a carboxyl functional group.
Okay.
So, and just like a ketone is just a general term for like, a double bonded, like a carbonyl attached to like something that isn't like a hydrogen.
Mm-hmm.
But acetylation is a specific just carbon, So it doesn't. It would just be like another like a carbon. It wouldn't be like a long thing attached to it, and it comes up in like everything, like acetyl CoA,
Mm-hmm.
and in like epigenetics.
Mm-hmm.
Yeah. Oh yeah, and then another thing. So like the reason acetyl groups come up a lot is because they are just two carbons.
Mm-hmm.
So, like essentially, like they just wrote the R but for it to be acetyl, it would just be one carbon, like a CH3 there.
Mm-hmm.
And when that gets oxidized, it turns into CO2.
Mm-hmm.
So that's why acetyl is a good thing to know. Like basically all, like the oxidation or the breakdown of proteins, fats, and carbohydrates, they all converge at acetyl-CoA.
Okay. That's true.
Mm-hmm.
That is true.
Oh, and then you said, why don't they call it like a ketone? Because usually if you talk about turning something into a ketone, you're changing something and like in the structure and turning it into like a ketone, but acetylation is the addition of an acetyl group.
Okay.
So nothing is replaced, it's adding it. It's adding like that acetyl group.
That makes sense.
Mm-hmm.
So this one, I had a hard time understanding.
Mm-hmm. Yeah,
so PK, is that PKA?
What's up?
Because it says PK, it doesn't say PKA.
Well, K could be anything, right? It could be, there's Ka, there's Kb, there's K equilibrium, there's K W. That all comes from like the law of mass action.
Okay.
So it's like a generalized term. So okay. I see like, two things that are just like going down, and then like the S sigmoidal one means like cooperativity, right?
Right.
So what are they saying? Okay. So the one with the highest PK, let's see. Oh, does it say in the passage anything about any one of these having a higher PK or something?
No, you have to go about the passage.
Okay. Data. And then this CD signal, is that like okay, so that's the pH dependence of the denaturation, so unfolding, right?
Mm-hmm.
So, okay. Let's see, 5-HMCWT seems to have the most cooperativity, unfolding cooperativity.
5H.
The one with this dotted line and circle, open circle.
Oh, 5HM. Okay. You said it looks like it has the most what?
Oh, cooperativity, just because it has that sigmoidal curve.
Yes. Uh-huh.
So okay, now I have to see if that's the highest PK or the lowest PK or the second highest. Wild type. Yeah. I mean, wait, so it doesn't say like anything else in that passage? I just need to know which one, because I need to see. Oh, there we go. Okay. Let's see. All right, so I motif, C-rich I motifs. Okay. Okay. Okay, so okay, I guess K in this case is just because K is always going to be, no matter what, a ratio of like products to reactants.
Okay.
So the higher the P for anything, like the lower the P, like if it's pH, pK, pKa, pKb, pKw, like pK equilibrium, it's like the lower it is, the stronger it is, or the greater its tendency to go make products.
So the lower the P,
whatever it is, right? Like higher pH means something dissociates more.
Mm-hmm. The lower the P whatever, the stronger it is.
Yeah. I would like, in my notes I always use like the proportionality like symbol.
Mm-hmm.
Looks like a Jesus fish. So I would write P like anything is proportional to proportional to like dissociation or something, or like product concentration.
Mm-hmm. Okay. So.
Now it makes sense because now I know that it's the methyl. So methyl stuff added to DNA causes it to wait, sorry. Methyl weight would make it fold more.
Yeah, it would.
Let's see. Hydroxymethyl. So, alright. Let me just take... So, wild type is how it is normally. And then it seems like it's shifted to the right for the 5-methyl... what is that? Cytosine?
Mm-hmm.
Okay. And then it's shifted to the left with higher, cooperativity because of the sigmoidal shape for the 5-hydroxymethyl cytosine.
Mm-hmm.
So the pH, they said the concentration of DNA is 3 micromolars. Let's see. That's the pH dependence of it. So, okay. So basically, we can think of pK as... Yeah, okay. We can think of it as like pKa, right?
Okay.
Because, think about it this way. Like, that pH value, it's going to... So, like, an acid would respond... So the stronger an acid is,
mm-hmm.
the more it'll start to react at a lower pH environment. Like, let's say the pKa... So, like, for the 5-HMC, it seems like... So, the normalized CD signal is, like, 1, and then it starts to change to less than 1 when the pH is a 6. So that means that its pK is going to be less than 6.
Okay.
Yeah. Now, let's see. And in the middle of each of these curves, right, that's like the equivalence point, aka when the moles of... When it's essentially going to be... I'm sorry. It's essentially going to be like when it's like half, like reacted and stuff like that. So I would look at that, and when it comes to that, right, it's like the normalized CD signal at 0.5. I would use that, and for that, it seems like it's the first thing that happens, or the 5-HMC wild type, like. At pH of 6, that's like the equivalence point. And then, like, going to the right, it seems like it's going to be the wild type, followed by the 5-MC wild type.
Uh-huh.
So the pK of the 5-HMC is going to be the lowest, followed by wild type, and then last would be 5-MCWT.
So the question is, so the 5-HMC has the highest. Okay, so what am I looking for? Like, so based off of the graph.
Yeah.
The unfolding cooperativity increases as I go to the right, correct?
No. So first thing to do is, for this, there are 2 parts, like 2 ways of, or 2 steps here. So the first step is identify which one has the greatest cooperativity, and that's
means that unfolds the least.
Oh, that just means that, so cooperativity, right? means that as something starts to happen, like it changes conformation, like it changes the shape. So you're going to see a sigmoidal curve there.
Right, and the only one that has a
Yeah.
significant
So
is
we
5.
so we were able to determine which one has the highest unfolding cooperativity right away. The second thing that we had to figure out was, is this is the 5-HMC one? Is it the highest PK, the lowest PK, or the second highest PK?
And it's the lowest, the high.
It's the lowest PK because it starts to
Okay.
unfold at a lower pH. So
Ah,
it means that its PK, it starts like its equivalence point for unfolding is at a pH of 6, right?
yes.
Which means that its PK has to be less than 6.
Okay.
Because in a pH of 6, it's in a basic environment relative to what its PK is.
What are the rules for like pKa greater than pH? Something about positive or negative.
Oh, just like, if the. So, like, we can use, for example, like an amino acid, right? Like
Yes.
its carboxyl group or carboxylic acid group has a pKa of 2.2, and
Mm-hmm.
its amine group, it's like what, like 9 or something, 9 point
Mm-hmm.
something.
Mm-hmm.
So let's just pretend that we put it into some environment with pH of 0, right?
Dang.
So if it's pH of 0, um, and its pKa for the carboxylic acid is 2.2, the pH is less than the pK, so it's in an more acidic environment relative to its pK. So it's going to keep its hydrogen.
So it'd be positive.
Um, yes. Now
Okay.
let's start to raise the pH. So once we hit a pH of 2.2, it's going to lose that hydrogen, right?
Mm-hmm.
Because it's going to be in a basic environment relative to the pKa. And then let's say we raise it some more at like 7.4. It's going to be like the Zwitter ion because the carboxylic acid group is going to be negatively charged, and the amine group is going to be like positively charged, right?
Mm-hmm.
And then let's say we raise it to like the 9 something or whatever it was for the amine group, like 9.8
Mm-hmm.
or something. I forget exactly the number. So once the pH goes to the pK value of the amine group, then it's going to be at then the amine group is going to be in an environment that is relatively more basic. So that's when the amine group is going to lose, that um, whatever hydrogen or proton.
Okay.
So yeah, so the PK, like PK thing is the inherent value of the acidity of something,
Mm-hmm.
and the pH depends on water because it's really based on the autoionization of water.
Mm-hmm.
And so like pKa plus pKb would be equal to pKw.
Yes.
Mm-hmm.
Okay.
Yeah, and
And
like
then this.
how they normally tell,
What?
like we normally are taught like it's pH scale of like 1 to 14, but like in reality,
Mm-hmm.
like strong acids actually have like a pKa of like less than 0.
Yeah.
And you might be asking, how is that possible? How can it be less than 0? And that's when you do something like, if it's in a gaseous state, like hydrochloric acid as a gas has a pKa of like negative 5.2.
Lord.
Yeah. And then same thing. So there's super acids and super bases, and you've seen them before, but they just didn't call it that. Like think about in organic chemistry, something like that is a strong reducing agent, like a Grignard reagent, or like
Mm-hmm.
LiAlH4. Those things have
Mm-hmm.
like a pKb of like way, um, like it's no longer like that 1 to 14 scale.
Okay. That makes sense.
Yeah.
Um, so this one, I made an educated guess because I just pictured that, like, even if a wave went through stuff, the frequency would still be the same. But like, what's like the real?
Oh, I just wanted to say that strong acids generally have a pKa less than -2.
Okay.
And yeah, anyway. What, let's see. Microbubbles, okay. Non-toxic high molecular weight gas, SF4. Anyway, what are the following properties of a 2.3 megahertz ultrasound wave? Oh, which of the following properties of that remains unchanged? All right, so this is something to know, okay? So we know that. So even though they say that frequency is inversely proportional to wavelength, and you know when something enters into like a medium, like you know the wavelength changes, but the frequency never changes. Because think of frequency as a measure of its energy. Like you know how energy of a photon is equal to Planck's constant times frequency.
Mm-hmm.
So that never changes. Okay.
Okay, but everything else does, like amplitude, wavelength, even the speed can change, but not the frequency.
Correct. Because frequency, and you know, I remember when I first learned this, like 6 years ago, I was like, how can wavelength change and frequency not change? And it's just because frequency, we use it as just a value of energy, essentially.
Mm-hmm. So this one, yeah.
All right, so you know, you could just use the formula like for you know wavelength and you know wave speed,
which is v times wavelength.
You could just like if the speed is meters per second and wavelength is meters. Oh wait, sorry. Okay, you have to find the wavelength. All right, and that's the speed of sound, and we have the frequency of sound, right? The 2.3 megahertz.
Okay.
So basically, you know, like if you take the velocity and you divide it by the frequency, I think you would get it.
It looks like multiplication. Oh yeah, so you say I take the what?
Because all right, hertz is equal to 1/second. Because it's basically like number of cycles per second. So if you have 1,500 meters per second, and if hertz is also 1/seconds, if you multiplied them, you would just get meters per second squared.
So hertz is frequency.
Yeah, but it's like write down like number of cycles per second. So it's a hertz is equivalent to like the reciprocal of a second.
Okay.
Yeah, so that's why you would divide it to get meters.
Okay.
Yep.
That makes sense. That's what I guessed. This passage was hard, but I guessed on this one, and I got a good one. But I was like, because I thought the thing was Q equals C over V. That's flow. What's the flow rate equation?
Well, you know, there's different types. There's like continuity. There's like, but maybe you're thinking of like Poiseuille's law.
I'm just thinking of the one that we typically use for capillaries, so like cross sectional area
times velocity. That's a continuity one.
Okay.
But
so like
yeah,
I just knew that it had to be A times V, but then they started adding in and I was like, I don't know.
Yeah, so when we deal with capillaries, we deal with like the cross sectional area of like all of them. Because if you think about it, in order for there to be a continuity of flow from like let's say like an artery into like capillary, that the blood going from the artery like is going through a lot of capillaries.
Hold on. So you're saying when we look at...
Because capillaries have to be thin enough for, one blood cell to basically go in single file. So that one blood cell can diffuse gases with, the tissue. So, yeah, so basically, like, in order for there to be a continuous flow between, like, a blood vessel and capillaries, like, because, like, for instance, like, a vein and an artery, right? There could be, like, like, it could just go from a vein to, like, all right. If you want to go from an artery to a vein, there's capillaries in between. But it could be one artery to one vein. But the capillaries, since they're so much thinner, it has to be a ton of them. So that's why it says a capillary bed.
So that's why it's in.
That's why. Oh, you said N? Yeah, because it's a number of capillaries. So essentially, you would multiply it by that as well. So each capillary has a cross-sectional area of little a, and if there are n capillaries, you multiply it by little a.
Okay, so why can't it be big A, little a, n, b? Like, why is it over underneath? Why is it A over NA, B?
Oh, because like that's just for like a regular blood vessel, like an artery or a vein, where it's that one blood vessel and it has its own cross-sectional area. But when we're dealing with capillaries, it's the cross-sectional area of like all of them.
So I'm assuming that big A represents the cross-sectional area of all of them. But then to find the specific cross-sectional area of one of them, you would do big A divided by the number and the cross-sectional area for one of them?
Yeah, because big A is by default one blood vessel. Yeah. And for capillaries, it's going to be multiple blood vessels, like multiple capillaries. So that's why, like, the cross-sectional area A in the continuity, equation, the flow rate, continuity thing, would... So, they have that, like, written down there. You see how it says capital A times V is equal to N times little a, right? So the A part, and the U is just velocity, but that's why that's the only way that you can make the flow consistent or like continuous, because blood basically travels from like a blood vessel with capital A cross-sectional area, and then it splits into all these tiny little capillaries that each of which have a cross-sectional area of little a.
Okay.
So just think of it as like splitting into all those different little capillaries. So it has to be like the sum of the cross-sectional areas of all the little capillaries in order for it to equal the cross-sectional area of the blood vessel that it came from.
Okay.
So yeah. Does that make sense?
Yeah, it does.
Okay.
For this one, so I just looked on units and I was like, okay, well, it's going to have to be, something over something. So I was like, okay.
Okay,
I
so...
divided 10 to the 5th by 10 to the 3rd, but I kept getting 10 squared. And I was like, what the heck? That's 100. So, like, I just chose C because it was the closest thing to 100. But this explanation literally blows my mind.
All right, so basically, like, atmospheric pressure is, like, if I were to draw arrows, I would draw them going down on the water or whatever that, water. And when you open, like, the stopcock, it will push the water upwards into that, like, tube thing. And the pressure of that will be equal to the atmospheric pressure.
Okay.
And then you just have to see how far up it will go. So you can just... So let's see. Oh, okay. Since we want, meters essentially, right? We can just multiply these two. Because then... Wait, sorry.
Mm-hmm.
Newtons.
I divided.
Oh wait, so we need another value here.
Apparently so.
So, oh wait, no, that'll cancel. All right, yeah. So basically, we could take that density and let's see. You can take that density because density is mass over volume.
Mm-hmm.
Okay. All right, so you know like how the buoyancy equation or whatever, it's like the density of water or the fluid times the volume displaced times little g, right?
Little G. Uh-huh.
So the idea is, since it is a force and equals like a Newton, if you take density and you multiply it by volume, it just turns into mass, right?
Yes.
Yeah, and pressure is just force over area.
Mm-hmm.
So you could take that pressure value and you could multiply it by the area to get like the newtons or whatever. So basically, what you'll do is hold on. I think I do remember answering this one before, and I like drew it out. Let's see if I can. All right, whatever. Forget it. Okay, all right, so essentially, as it goes up, there's gonna be I would draw like the pressure of whatever. It's basically like going up because of like the atmospheric pressure pushing down around it, and it's then I would draw like a force vector going down, which is the weight.
Mm-hmm.
Yeah. So essentially, like I would take that. So like to find the weight of it, you can just multiply that, the density by the volume, and to get mass, and then you'd multiply it by, you'd multiply it by g to get the weight of it moving downwards, and then you would, okay. How far up the tube will it rise? Okay. All right, so you see where it says, okay, in the explanation, right?
Mm-hmm.
Does it make sense that that left part, right? It's basically just so okay, it's the density, right? Times h, which is the height, times area. Those things are like the h times capital A. That's a volume.
Okay.
Does it make sense that it's a volume?
Yeah, because essentially it's the volume of the thing that's trying to go up, right?
Because like area is like 2 dimensions, and if you just multiply it by the height, it turns into a volume.
Okay.
Yeah. And then, so that's the volume. So it's basically, the density times the volume times, it's like the, what's it called? Archimedes law, like the buoyancy one. Like P, like rho V G.
OVG. Is that the P? That's
Yeah, it looks like a P.
Okay.
Yeah. So that's what that term is, that expression is on the left, like, the density times the height times the area times the, 10 meters per second squared, which is G.
Mm-hmm.
And then, so that's going to, basically turn into, newtons, right? And then on the right side, you have the atmospheric pressure, right, times the area, which means that the meters squared will cancel. So Here, let's see if I could talk about, what was it? Bernoulli's equation. So it's not really like something, well, it's essentially just a means, well, actually, I don't know if that would be helpful, but like, do you know what I mean by Bernoulli's equation? It's essentially like the, here, let me send you this in the chat. It's essentially the conservation of energy applied to, like, fluids.
Okay.
So, yeah, see if you can open that thing, and then I'll kind of show you something. Oh, I put it in the chat?
Mm-hmm.
Okay.
Oh. Mm-hmm.
All right, so, okay, so you see how, so energy, so it's basically conservation of energy, right? And P is the pressure energy. There's kinetic energy per unit volume, and then potential energy per unit volume. So in the problem that we're doing right now, there's no kinetic energy because there's no flow of the fluid.
Right.
So we, cancel that out. And then we are just left with, potential energy per unit volume and pressure energy.
Okay.
So that's what we have. So essentially you would just have the rho GH1 is equal to P2.
So that's why it comes into...
Yeah. So that's why you have, the rho, which is, 10 to the third, times, the H, times, the area for the volume, times G, and that's equal to the pressure times the area. And then the areas cancel, because, we don't know what the cross-sectional area is of that tube.
No.
So, it's just going to be equal on both sides, so they cancel, essentially.
Mm-hmm.
And then you're just left, and then you can just solve for H then. Because then it'll just be the pressure divided by density times G.
What's G?
Oh, little g?
Mm-hmm.
No, little g, right? Like, 10 meters per second squared.
Oh, okay. That makes sense. That's where it came from. Okay.
Oh, I found it where I go over this. Here, I'm gonna share my screen for a sec.
Okay.
All right, do you see it?
I'm waiting.
Right? You see it now?
Mm-hmm.
Okay, so downward is like the atmospheric pressure.
Uh-huh.
And then when the stopcock is opened, that atmospheric pressure pushes the fluid upwards.
Okay.
So I wrote over here, it goes upwards, so I wrote rise. And then you get, like, this, let's say it goes up to that level, right?
Mm-hmm.
So that's why I basically drew, like, a free body diagram. So up, that the vector going up is is a force caused by the atmosphere.
Okay.
And going down is the weight. So I wrote mg.
Mm-hmm.
And this entire thing, and then, it goes up by a height of h. So I basically just wrote it has a potential area of mgh, right?
Right.
Yeah. And then over here, right? So this is just like you don't have to do this work, but it's just me, like, explaining it. So, like, the density of H2O, right? It's 1e3 kilograms per meters cubed. And in green, this is just, like, something that we express in physics to kind of express, like, a property. So, like, for instance, like, volume is essentially, like, a length cubed. And, like, area is, like, a length squared. And h, which is height, is just a length, right? So,
right.
so this is, just mass over volume. And then, the atmospheric pressure, it's this, which is just a force over the area. Right?
Okay.
And so, going from here, I can just, since this is equal to the mass times the volume, if I take this and I multiply it by the volume, I get the mass. Right? And the pressure is a force times force over the area. So if I take the pressure and multiply it by the area, I get the force, right? So that's what's here. The atmospheric pressure times the area is equal to the force. So now I have a value for mass, which is 1,000 kilograms, and 100,000 newtons for the force, right? And this is how I got them. And so I can just plug them in for this, because this is mass times g. So see, I have the force, which is this, and then I have the mass, which is this, and g is the same, and now I can solve for height. So I write, the atmospheric force is, 1e5 newtons. The force of gravity, aka its weight, is the mass, 1,000 kilograms, times g, which is just 10 meters per second squared. So I get 1e4 newtons. Right?
Yeah.
So then I do the F net is equal to the sum of these two vectors. So since one is going in the opposite direction, it's like negative. So atmospheric force minus the gravity one. And I basically know that it's going to be greater than 0. Because this is larger than this. So it's going to be larger than 0. Like the net force is going to be going upwards until it rises to height of h. At which point, the atmospheric force is going to be equal to its weight. These are going to be equal. So at that point, it's, F net is going to be 0. So I wrote in red over here, at first, the force caused by the atmosphere is greater than, its weight. So the water moves upward until it reaches a point where, these vectors are equal to each other. Right? So, then I write, you can use potential energy is equal to mgh because energy is conserved. So h is equal to mg when mg is both equal to the atmospheric force and that the force due to gravity.
Okay.
Yeah. So this is just me going over it whatever conceptually. Make sense?
Yes.
Yep. Oh, this is me going over it with your friend. So I can see some stuff that we had before, like this thing. And then this thing over here. H2O2, remember this question? If lysine is a product of the active site. All right. Anyway, yeah. And then this is how I did the stability of that question with the 5MC, the wild type 5HMC.
Yeah.
And then here's where I say pH is less than the PI and stuff. Okay. Oh, and then this is another question that we just went over. One blood vessel, right, has a cross-sectional area of capital A, speed of V, but N blood vessels is the area, a speed, I don't know why I wrote that. Anyway.
Another question I have for you is, what would you suggest would be the best way to memorize or conceptualize, glycolysis, Krebs, PPP, gluconeogenesis? Should I just continually write them out every day?
Oh, here, I'll share my screen again for that. So okay. I have this thing, which is kind of me going really crazy with everything in one doc. This is the cell. This is yeah. So I was trying to figure out how that works because basically here I have it. This is the one for you. Here. So the thing is that all right, so for you, like you would have to go to this notebook area and hit more notebooks, and then it'll go through like the stuff that I shared with you, so it should work through there.
Yeah, I was able to add it.
Oh, you got it to work?
Yes.
Okay, so yeah, this is your notebook, right? And this is, where the metabolism stuff is. But then I
Okay.
also have this like brain dump over here, which is
Mm-hmm.
kind of like, me like simplifying it. So
Mm-hmm.
so basically catabolism is oxidation, which
It's
is the production of energy.
uh-huh.
So here I wrote like proteins get oxidized or broken down into amino acids and then into alpha keto acids, but blah blah blah, essentially acetyl CoA. Carbs, blah blah blah, acetyl CoA, fats, blah blah blah, acetyl CoA, right? And then the acetyl CoAs is a thing that gets combusted, like in a combustion reaction,
Mm-hmm.
right? And all the carbons get like lost as carbon dioxide. So basically, I wrote all converge to acetyl CoA. So that means, and then all end products or waste converge to either, ammonia, CO2, or like H2O.
Hmm.
And so this is also good to know. Do you see this right here?
Yeah, that's the reduction and oxidation.
Yeah, yeah. So like, something that's a single bond, if you go to the right, oxidation via, these things.
Mm-hmm.
It turns into a double bond and then it'll turn into an alcohol. If it turns into a tertiary one, it can no longer be oxidized. If
Right.
it turns into a secondary alcohol, it can be oxidized into a ketone but can't go any further. If
Mm-hmm.
it's a primary one, then it can be oxidized into an aldehyde and then a carboxylic acid, and then that guy gets lost as carbon dioxide.
Mm-hmm.
And I just wrote some additional things like PCC can turn into that, but like something that's a strong oxidizing agent like KMNO4
Mm-hmm.
would go straight to this, the carboxylic acid.
Okay.
So this is useful. I remember there was a question asking about like hydroquinone or hydroxyquinone or something like that, and I remember like this was helpful in that. Let's see. Oh yeah, so for like glycolysis, like all right, so generally speaking, you'd memorize or know the irreversible steps, and then
Okay.
it helps to know why they're irreversible, right?
If you
So
add in ATP,
wait, what's that?
it's because ATP is added to like it's
Well,
adding. No.
well, that can't really tell you much, but check this out. So for glycolysis, right?
Mm-hmm.
Glucose can go freely back and forth into the cell, right?
Mm-hmm.
So this first irreversible step is to trap it in the cell. Because once it's phosphorylated, it has a charge. And if it has a charge, it can't go through a lipid bilayer. So you see how I wrote like it can't go out? Like this is like a can't kind of like symbol.
Yes.
So it's trapped in the cell, right?
Mm-hmm.
So now what happens, right? So like glucose 6 phosphate, it can go through the glycolysis pathway. It can go through the pentose phosphate pathway to make electron carriers or DNA. It can be turned into glucose 1 phosphate, which can go through, glycogenesis to make glycogen, or it can turn into like gluconeorate, which is like carbohydrate synthesis. AKA
Mm-hmm.
all this stuff is anabolic.
Anabolic means make.
Yeah, and
Okay.
therefore a reduction.
Anabolic reduction make. Okay.
Yes. Ana, I think, means up. Kata means down in Greek.
Okay.
So basically, what's the point of this second irreversible step? It's to trap it into a catabolic pathway.
Mm-hmm.
So like knowing the why, like there's like a quote by Nietzsche that says, as long as you have a why, like it doesn't matter what the how is. So instead
Okay.
of like memorizing everything, if you know why it does something, because look, the second irreversible pathway, what's the point of it? It's to trap it into catabolism because, fructose 6 phosphate can go into the anabolic pathways, right? But once you phosphorylated and get like 1,6 biphosphate or bisphosphate, like it can't go into the anabolic pathway. So then everything else is not really that important. So I wrote like this double arrow that says stuff until it gets to PEP. And then this is the third irreversible step. So why is that? PEP is an enol, which is less stable than the keto tautomer. The keto tautomer is the pyruvate.
Okay.
Yeah. And then I wrote this thing out, and I said net gain of everything except for NAD+. NAD+ is replenished in fermentation and the electron transport chain.
And PPP makes NADH, not NAD+.
NADP, you mean?
NADP, which can go into glycolysis.
So NADP is involved usually, or you'll see it. Wait, what the? I don't know where that went. You'll generally see it in anabolic pathways. So, like for instance, right? Oh, and then you mentioned 2 electron stuff, right? So, like nicotinamide, aka NAD, right? NAD plus or NADP plus. They involve a hydride shift. That's an H with 2 electrons, so that's why it's an H minus.
Okay.
And it transfers 2 electrons. So remember when you asked about that reaction that transfers 2 electrons? Yeah. FAD is like flavin or whatever, and it can be either 1 electron or 2 electrons. Yeah. And then CoA, right? Like what does it do, right? It activates acyl groups for transfer by a nucleophilic attack, and it also activates the alpha hydrogen of an acyl group, so it can get rid of that proton. And it also has like a thiol group, so it can form thioester linkages. And then this is me, going over like the TCA cycle essentially, and these are like the the irreversible steps. So like all the other stuff I just write stuff, but I think it's useful to think of each of these things as like however many carbons there are. So like it loses a carbon here, a CO2, to make a 5 carbon compound, loses a CO2 for a 4 carbon one. Yeah, so I kind of like go over. I don't know why it's not like loading or something, but like yeah, I go over like several pathways here in like a very like simplified way. So yeah, do you have like any like questions like in particular? Whoops.
Oh no, because I was just making I'm not saying that's my strongest suit. I have an okay understanding, but I know I spent a lot of time last year literally memorizing each process with all the stuff that's in third, and like not a lot of questions, barely any questions come up on the MCAT about the specifics. So I was trying to learn about like, okay, what specifically do I need to know besides
Yeah, I have that. Yeah, in the like, so I have like the full thing in the metabolism one, and then like, like a simplified version in the brain dump. Gluconeogenesis, right? And I draw, and like the things to know are like the ones that are like in this color, like magenta or whatever. I don't know why it's not like loading the other ones.
I guess that during the tutorial time, maybe I should write down not only my equations, but maybe like some of the.
Oh yeah, totally.
Okay.
Yeah, and then I also shared with you guys like some textbooks that I use for like content review that are really like great. Like I have like this Malek Cell book. This is an excellent like anatomy and physiology book that talks about things like in a really like cool way. This is a really good like physics book, and this is like a really good biochem book over here. So like whenever if I wanted to know about like gluconeogenesis and stuff like that, I would use this and just like so like this is kind of like what I drew over here, you see?
Yeah.
So I would draw like things like that, I suppose. Yeah, just like I would like learn not like obviously like not every pathway in every system, but how things differ. Like if I
Okay.
wanted to learn about gluconeogenesis, I would think about it as reverse glycolysis, except it's not.
Yeah,
At
exactly. Like it is, but it's not.
Yeah, like it. So basically, it's the parts of it that aren't reverse glycolysis are clearly then going to be the irreversible parts, right?
Okay.
I also talk about it here, gluconeogenesis over here. So essentially, three carbon precursors, lactate, alanine, and glycerol, turn to pyruvate in the mitochondrial matrix of liver cells or in the
Hmm.
cortex of the kidney. So essentially, um, what did I? Oh, it kind of like got mixed up over here with this like ratio. So, oh, and then I talk about some other stuff here, but and then over here I think I have like polymerization.
Oh yeah. Ooh yeah. Mm.
Oh yeah, yeah. So all polymerization are dehydration synthesis reactions, which are
Which
also
means
known as
one
condensation,
more. Okay.
and they
Hmm.
require an energy input. So an example of something is like I can if you like can see like how this makes an H2O, right? An H from something and an OH from another thing
Hmm.
turns into like that gets removed and turns into H2O, and then that bond is made.
And those are esterification.
Wait, oh yeah, yeah. You have this ester bond, which is can also be known as a glycosidic bond.
Okay. And then for hormones, again, should I just purely memorize it or like, oh, is
Um,
your attacking
yes.
the
So like first like classify the category. So like do everything like make the categories for things
yeah, like
first.
where they're from,
Wait, sorry.
like where they're secreted from.
Oh no, just categories as in like um like fat soluble.
Oh, so like steroid versus lipid.
Yeah. So like
Like
a steroid hormone, like how would that work?
steroid hormones, they're hydrophobic, so they can go through the membrane easily, and then they attach either on the nucleus membrane, and they
Well, they can go through like the nuclear membrane too, right?
yeah, they can do that too, and then
So they'll
they
go
can bring about
directly. Mm-hmm.
transcriptional modification,
Yep.
and then lipid hormones, they're hydrophilic, so they need uh, to bind the receptors on the membrane, on the cellular membrane, and
Yeah.
secondary transport's big for that, right?
Yeah. So there'll be a second messenger, right? And
Yeah.
remember,
And
I think did we go over like how there's like a G protein one, but there's also like a tyrosine one and stuff like that.
hmm.
Yeah. Um, so okay, like I have like because I remember like memorizing the hormones wasn't too bad for me since I was able to do that, and I can scan this out because I go over like every like all right, so like all right, if you can see that. Whoops.
You have to like unshare your screen so I
Oh
can
yeah,
see it better.
here.
Okay. Yeah. Does that have all the? Okay. Mhm. Mhm.
Um,
So yeah, it's basically all the glands and stuff. Okay.
yeah, and then um,
Okay. The okay. Mhm.
yeah. So basically, like um, so like so like for instance, like adrenal cortex, right?
Yes.
What type of hormones would that make?
Um, the adrenal cortex. Ooh. Okay. Okay.
Like, just tell me if it'll be like water soluble or fat soluble.
Oh, those are lipids.
Yep, because they're like steroid based, right?
Oh, what? Wait. Okay. Hold on.
Mm-hmm.
Adrenal cortex. I'm thinking of adrenaline, so it's norepinephrine and epinephrine, which I forgot
Well,
their word.
in the cortex though, right?
So not the medulla.
Correct.
So this is the cortex. So okay, so it's it's cortisol
Mm-hmm.
and corticoids like mineral
Mm-hmm.
corticoid and
Yep.
so
Yeah.
it's cortisol and what was the other one?
Aldosterone.
Aldosterone, which are both uh,
Yep.
are steroids.
Yep. Good. And then the adrenal medulla would have epinephrine and norepinephrine.
Yeah,
And
and
then,
they're
yep.
weird name. It's like a weird classification name specifically for those two.
Um, what do you?
Ooh, it's like
Well, I like a peptide.
it's like a specific name for those two.
Oh,
Because
catecholamines.
yes, catecholamines.
Yeah, so like certain neurotransmitters are also like that. A catechol is a benzene attached to two H's. I mean, sorry, two OH's.
Mm.
Yeah. Hypothalamus makes all the releasing hormones.
Okay, so hypothalamus, they do is that they do the ones that affect the hormone. So hypothalamus, they have the GnRH.
Yeah. So they essentially have releasing hormones. So they're either going to so they're going to send so they're going to make releasing hormone because that's where like the relay center is. So it's going to be like, "Oh, crap, I need to tell these guys to do this." So
Mm-hmm.
it'll make releasing hormones which will go to the either the posterior or the anterior pituitary gland, which will
Mm-hmm.
and those will make the actual hormones, which will then
Right.
go where they need to go.
So the hypothalamus is the part of the HPA axis.
Oh yeah, yeah. Mm-hmm.
Okay.
Yeah, so essentially, just they make the releasing hormones.
Releasing hormones, which
Yeah,
is GnRH and ACT. No, there's another one, but I forgot it. I know it's GnRH.
Basically, just think about any other hormone, and it's that but releasing. So like thyroid releasing hormone, like thyrotropin releasing hormone, corticotropin releasing hormone, gonadotropin
Mm,
releasing hormone, prolactin releasing factor. So just think
mm.
of like the stuff in like the anterior or posterior pituitary gland, but like before it.
Releasing. Okay.
For the anterior pituitary, I use the a mnemonic device flat peg.
Yeah, flat peg. Uh-huh.
Yep. So that is pretty much like most of them. The
And to
yeah.
clarify, with aldosterone and ACTH, I know they both increase water absorption, but I know that aldosterone specifically causes increases of sodium absorption and potassium, decrease of potassium absorption. It's just that I get confused on what specific areas in the kidney that they affect. I
Yeah.
forgot, like,
So
yeah.
I have this thing that I can send you. I sent it. So basically, I go over like the blood volume and how that affects.
I would need that because they asked some osmotic questions that were like, I struggled through them, but like I want to make sure I know them better because like I had to think really hard.
Yeah, I wrote it in something like for galvanic cells, I think. Yeah, in your notebook, content two, like Roman numeral two. So here, I'll share my screen. So so over here. So like okay, we can go through it. So because like I wanted like when I wrote this out, I wanted to be very specific and differentiate blood pressure from blood volume. So
Yes.
let's say that we have dehydration or a decrease in sodium concentration or like a hemorrhage, right?
So dehydration specifically, I know is a net loss of water, but it can also be a decrease in sodium.
All right, so check this out, right? Um all right, so dehydration is a net loss in water, right? And
Yeah.
osmolarity will increase because the sodium levels will stay the same, but if you have less of the volume, its concentration will go up, right?
Okay. Pause.
Yep.
So they like to ask questions like, I get confused with like blood, cell. So it's okay. The osmolarity of what, like, so when I know that there is more solute, so like say we have an influx of sodium in the blood, I'm thinking that now the cells are in a hypertonic solution,
Oh
so
yeah, don't.
the water will be come out.
All right, so don't think about that. Here, check this out. Think about here this. So think about this over here. So this is a blood vessel.
Okay.
So the pressure that water or blood or something exerts, right, against the walls of the artery is a hydrostatic pressure.
Mm-hmm.
All right? Which means it's like a pushing. Think of it as a pushing type of pressure.
Okay.
Now, osmotic pressure is the opposite. That's more of a sucking kind of pressure.
So hydrostatic pressure is not osmotic pressure.
Yeah, they
Osmotic
are
pressure,
opposites.
osmotic pressure refers to solutes.
Yes.
Okay.
So, when you're making pasta, for instance, like you know when people add salt.
Yes.
So, I remember in like whatever like elementary school or whatever, people always said it was to raise the boiling point.
Yeah, I still believe that.
Yeah, so that actually doesn't really do much to the boiling point, but what it
Oh,
does is it increases the osmolarity and thus
okay.
osmotic pressure. So the pasta is going to absorb more water. It's going to suck up more water.
But that's weird because if the pasta is in a hypertonic solution, because there's a lot of solutes
Yep.
in
So the
water.
water will go into it, right?
No, because with
Oh wait,
osmolarity,
sorry. Wait. Okay, I see what you're saying. All right. Well, actually, the pasta itself is
mm,
not anything because it's solid essentially.
mm,
So, it if it's hypertonic, isotonic, hypotonic, it's like so the pasta itself doesn't have any water in it
right.
at first, right? It's completely solid.
Mm-hmm.
Yeah. So you know, so the usual thing about osmosis isn't really happening, but there is going to be an osmotic pressure,
Okay.
and that is going to be going into the solid pasta.
Okay.
But but like in general, like in the kidney, for example, the hydrostatic pressure, like when it's at the glomerulus or whatever,
Mm-hmm.
um, the hydrostat like it's the hydrostatic pressure is what forces the blood through like the uh.
The hydrostatic pressure
Mhm.
forces the blood into the glomerulus,
Yeah.
not the osmotic pressure.
So, oh yeah. Because it's think of the hydrostatic pressure as pushing
Okay.
because it comes from that fluid itself, and the
Okay.
osmotic pressure is like a sucking.
Well, the glomerulus doesn't suck it in.
No. It's less. It's more just the pressure that put because it's kind of like a strainer,
Mm-hmm.
and so you want it's like your blood pressure pushes into that strainer to get it to go to like the glomerulus.
Mm-hmm. So when you have proteins in your urine, that means that you have high blood pressure because now it's like anything can come in.
Oh, because that okay. So now that involves some other stuff. Like it involves. So I kind of have the diagrams of that here.
Mm-hmm.
Like so, if you have a damaged filtration barrier, then the proteins can cross through. Because normally they're fenestrated, which means that there's like openings, like windows, like
Mm-hmm.
this right here. So this is like basically a close up of like the glomerulus over here,
Mm-hmm.
and it's a fenestrated membrane, so there's openings. So small things can go through, but plasma proteins don't because they're too big.
Mm-hmm.
But if they're damaged, like leaky, right, then plasma proteins can go through. But in
Okay.
terms of hydrostatic pressure and osmotic pressure, the hydrostatic pressure, right? See how I'm kind of drawing this like this? It goes outwards into filtration and eventually urine.
Huh?
Yeah. And osmotic pressure, as that increases, it goes back towards the blood vessel. So it's reabsorption and back into the blood. So, like,
Okay.
here's like a kidney, and like the outer portion here is a cortex, and inner portion's the medulla. And as you go from the cortex to the medulla, your the solute concentration increases, which means that osmolarity increases, which means that H2O gets reabsorbed.
Yes.
And
Wait.
yeah,
Because right, yeah, because it flows to high solute concentrations.
mm-hmm.
Water. Mm-hmm.
Yeah, and so less of it will be in the filtrate. So that's why you have like, where is it? Like here, cortex. Yeah.
Is the water it allows water, and the ascending is for solute.
Yeah, so the descending one happens to be permeable to water, right? So as it's going down over here, it's entering into a higher osmotic, like more osmosis will happen essentially. So
Higher osmotic pressures in the
mm-hmm.
descending. Okay.
Yeah, and then as it goes back up, like it's going to like lose some salts.
Okay.
And yeah, so basically, like, as we go from the cortex into like the medulla, salt concentration increases. So but oh yeah, then I have another like kind of diagram here. So like reabsorption of water, and then here reabsorption of sodium and chloride because we're going up.
Okay.
And yeah, I have like various things here.
I'll
Collecting
make sure to
duct.
look at these because, like, okay, I see what you're saying.
Yeah. So and then yeah, back to this. So I wrote everything out just to be detailed because I wanted to separate pressure from volume because they like for instance dehydration means that there's a reduction in blood volume, which means that there's a higher like even the number of solutes doesn't change, the concentration of solute changes, right?
Number of solutes doesn't change, the concentration does. Okay.
Yeah. And so that'll lead to reduced blood volume, which means that the pressure is going to be lower. Whereas if we had a decrease in the sodium concentration, then it's going to be like the volume will stay the same, but the pressure will go down because we have a lower solute concentration.
The osmotic pressure will go down.
Yeah.
Okay.
The osmotic pressure will go down, and then that'll be reflected in the blood pressure. Yeah.
Okay.
So basically, I separate it because like think about like I start from like its detection. So I have here arterial baroreceptors. Right. That's what can read if there's a change or detect if there's a change in the change in the pressure. And then the juxtaglomerular cells of the kidneys, that's what can detect a change in like osmolarity essentially.
Okay.
So let's say that it notices a change in the pressure. It'll send that signal to the hypothalamus, which will send like a releasing hormone to the posterior pituitary, which will then secrete ADH, antidiuretic hormone, which will go, into the kidneys, particularly like the collecting duct, I think. The end of it. Like, I also think of it as always drilling holes. So it basically opens up these holes in the collecting duct of the nephron. And that means that there's going to be a reabsorption of water which means blood volume will go up, right?
Mm-hmm.
Now, if it detected, lower osmolarity from not enough sodium, then it will release renin. And the liver, which makes angiotensinogen, once angiotensinogen combines with renin, it turns into angiotensin 1, at which point your lungs, remember how they said COVID, attaches to the ACE2 receptor?
Uh-huh.
That's the thing in our lungs. And that's why with people who have cardiovascular issues, right, they're going to have more of those receptors, the spike protein attaches to that. Because, ACE is angiotensin converting enzyme. So that's released by your lungs. And it takes the angiotensin 1 and turns it into angiotensin 2. And what that does is, to the arterioles, it causes a vasoconstriction, which raises the blood pressure. So that's why I wanted to differentiate between blood pressure and blood volume. Because increase in blood volume will cause an increase in blood pressure, but you can have an increase in blood pressure without changing the volume if you vasoconstrict.
Right.
Yep. And
okay.
And then if angiotensin 2 works on the adrenal cortex to release aldosterone, which works on the kidneys to reabsorb sodium. And,
yes.
Through that process, also water, and it'll remove, secretion means, it's going to go into the urine, potassium and H+.
Mm-hmm.
Yeah. So this is all of that stuff.
Okay. Those are all my questions for today because I'm still going through things. But I'll definitely make sure to look at the notebook because Thank you for sending today.
We still have 10 minutes, so we can go over whatever else you may have. Maybe
quick psych social. I haven't really gone through it yet, but we can go through some of them. Because I average 127s. I don't know what else I need to do to get better at psych social.
Were there any other questions in the other sections?
Let's see. I'll pull it up. I think there's okay, we could do. Okay, let's see. I can share. So this one was a little interesting. I just wanted to see how you would think about it.
Yeah. Let's see. Based on the passage, overexpression of which protein is associated with those cells becoming cancerous. So I'm just going to look for each of these. So let's see. G-flip. Where is that? It might be above that. Because I don't see G-flip.
Oh, okay, hold on. Sorry.
Caspase 8.
I'm gonna get it from here.
Okay.
I think. What's this question? Okay. Let me find it. This is bio. This is bio. Okay, it's this one. It's 17. Oh, review. Okay, here it is.
Okay. All right, now I see it. So we got caspase 8, protease that triggers apoptosis. That seems like pretty much the opposite of cancer. Let's see. C-flip is similar to caspase 8, lacks catalytic activity, controls fast signaling downstream of FADD. They think that it binds to it at the same site, and then it causes that thing to happen. Oh, wait. Sorry. all right, I'm just gonna. So FAS is a receptor involved in apoptosis, which is opposite of cancer. When it's stimulated, it causes FAD to be recruited, which then takes out procaspase 8, which is converted to caspase 8, and then it causes apoptosis. So that's like, so I would like write out like in like arrows kind of. Here, I'll do that. So like I would write, yeah, so I'll, like I usually take notes of like pathways and things like that using like an arrow and stuff like that. And then let's see, fast activation doesn't always do it, so it can also activate this transcription factor, and then C-flip. So okay, let me just see the choices so I know which ones to pay attention to. Alright, C-flip, caspase 8, FAD, and FAST. Oh, okay, I think I already read those. So basically FAST, oh, it's okay. I think I have it.
Oh, okay.
Let me see. So okay, FAST, let's see, FAST turns or recruits FAD and caspase 8 to cause apoptosis, right? Which is the opposite of cancerous. And then C-flip I have to look at. But all those things are kind of like apoptosis, right?
So you're saying FAST, FAD, and capsate?
Yeah, because FAST is like the receptor for it, and when it gets activated, like some ligand binds to it or whatever, it recruits FADD, and then FADD causes the caspase thing to turn, like the procaspase thing to turn into caspase 8, and then caspase 8 causes like the apoptosis. So that entire like system works towards apoptosis.
Ah, that makes sense. So if I would have just understood that, then I would have been able to pick A automatically just because these are all into apoptosis.
Yeah,
okay.
Now let me just check out where C-flip is. C-flip, okay, C-flip. So okay, it looks like caspase 8, but it doesn't do what caspase 8 does, which is cause apoptosis. Then it's right? And okay, but yeah, you kind of see it. So like FAS is the receptor, and when it's stimulated, it recruits FADD, and then FADD turns the procaspase into caspase 8, and caspase 8 triggers apoptosis. So all of those things work together towards apoptosis.
Okay.
And then I see C-flip. It's just a version of caspase 8 that doesn't work.
Oh.
So imagine like, this entire system without the caspase 8. It'll be like, it's structurally similar. It would be like competitive inhibition, right?
Oh, so it would be binding more than caspase 8. There's an increase of it, which will cause activity.
And it's basically a broken version of caspase 8.
Okay.
Make sense?
Yeah, that makes sense. Because I was like, what? This is this one.
Butyrate. So this is like ketone bodies, right? The brain can only use glucose and ketone bodies.
All right.
And ketone bodies are produced when you're in extended like fasting state.
Yes.
From like fats.
Acidosis if you're fasting too long.
Wait, what's up?
Acidosis can occur.
From
too many ketone bodies being produced.
I don't know actually. Like you said, acidosis, like in terms of like your blood being more acidic.
Yeah.
I don't think so, because like I associate that with like too much carbon dioxide.
I think it does happen. I think it does happen.
Yeah, but that's a respiratory acidosis. There's a metabolic acidosis. Metabolic acidosis. That's when you have That's when you have either increased acid production or loss of bicarbonate or a reduced ability of the kidneys to excrete acid. I don't see anything necessarily about ketones, but okay, let's see. If HDAC inhibition by beta hydroxybutyrate is a physiological response in living animals, the information in the passage indicates it's likely to occur when this is sustained fatty acid oxidation.
So fatty acid oxidation occurs when the body's fasting.
So like essentially, like, you know, your body will first use the glucose that's in your bloodstream, and then it'll start to break down glycogen into glucose. But as it does that, it's also going to start breaking down some fats. So like the ketogenic diet is kind of like a diet where you eat you essentially don't eat like any carbs because you don't want your body to break down, you know, the glycogen and stuff, and you want it to just break down fats. And so like the ketogenic diet, like it takes also a long time for your body to be in ketosis because it means that it's going to have to be a prolonged period of that fatty acid oxidation.
Wow.
And
so what is the Cori cycle?
What's up?
The Cori cycle?
Isn't that in plants? Or maybe I'm thinking of the Calvin cycle. Cori cycle is like something where ATP is made or something. Cori cycle. It's just a lactic acid cycle.
A lactate. So Krebs? No.
No, like, you know, if they're so like lactic acid cycle is, you know, when pyruvate is made, if there's oxygen, it'll go into Krebs. If there isn't, it will go into fermentation to make lactic acid, and in yeast or whatever, it'll make ethanol. And the purpose of that is to replenish the amount of NADH. Or no, NAD plus. Yeah, so basically it's in the metabolism section of the notebook. So basically pyruvate can go into the mitochondria, but if there isn't enough oxygen, it turns into lactate and it produces NAD plus.
Okay.
So it just replenishes the amount of that electron carrier.
Okay.
Yeah. So okay. Now yeah, so all right, they said that it's prolonged exercise or starvation, right? So, and then after 8 hours, blah blah blah. So, sustained fatty acid oxidation. Nothing's happening with pentose phosphate. Yeah. So yeah, keto genesis what am I talking about? Keto, yeah. So that thing is basically so I have that in the metabolism brain dump. So fatty acid oxidation, basically fatty acid gets okay, sorry. And then so fatty acids break down into glycerol and acetyl-CoA, and acetyl-CoA can enter the TCA cycle that happens in the mitochondrial matrix of adipose cells. However, in the mitochondrial matrix of liver cells, the acetyl-CoA, which is an easily transportable form of fatty acid, so, two CoAs condense, another CoA is added. Let's see. And then that turns into beta hydroxybutyrate and acetone.
Okay.
So yeah, just you can remember that with I don't know if you can think of like the ketogenic diet and how they essentially require you to eat a lot of fats, and you know this is like that biochem like textbook here, so this pretty much talks about it. So like ketone bodies are a significant source of fuel and energy for certain tissues. So most of the acetyl-CoA produced by the oxidation of fatty acids in liver mitochondria undergoes further oxidation in the TCA cycle, right? However, some of the acetyl-CoA is converted into acetone, acetoacetate, and beta-hydroxybutyrate through ketogenesis. And yeah, it's funny. Beta-hydroxybutyrate doesn't even have a ketone functional group. But this is what happens in the liver, not in fat cells. And during periods of starvation, ketone bodies may be the major energy source for the brain.
Yes.
And, that's where it happens. And I guess these are some, pictures of it. Okay, and then here's, what's happening in the cell over here. So, yeah.
Okay. I'll make sure to look over all of the things that you sent me because they look very helpful. The slides, not the slides, the notebook. But yeah, that was just pretty much all the questions I have for today, and I'm gonna keep chugging along. Yeah, I'm taking another practice day on Saturday, so maybe it really depends. I don't know. Yeah, maybe Sunday, probably if you have time Sunday.
Yeah.
Okay.
We can do that.
And, yeah.
Yeah, some of these, see if, the textbooks can be useful. Well, maybe not, but they have some, extra kind of information and stuff. Well, actually, I don't think you need to do that. but, yeah, they have some pretty cool, information here. I see, whatever. They have, foundational biochemistry, so just things to know, anyway, whatever. Okay.
I'm gonna Venmo 100.